So let us start the 5th session of ISMIR. So we have 16 presentations in this session, and the first one is a candidate for best paper hours, and this presentation will be 10 minutes long. Keyboard temperament estimation from symbolic data, a case study on Bach's well-tempered Clavier. So the presenter is Peter van Kranenberg.
Thank you. Great to see you all. So indeed, this project is on keyboard temperaments. I did this work together with Gerben Bisschop, who is currently finishing a PhD thesis on temperament in our group. So this is the layout of a Western keyboard, and it has a problem. The problem is there are only 12 keys, but we need actually more than 12 pitches to play all intervals in tune. And this has two causes. One is that the keys are reused for different pitch classes. So as you can see, we use the same key, for example, for D flat and C sharp, etc. But even for a single pitch class, you need different versions, so to say, to play all intervals in tune. So this is basically the problem. It is impossible to choose the 12 fundamental frequencies for the 12 keys, such that all intervals and chords you play on the keyboard are in tune, are pure. The modern solution to this is to make the distance between the pitches for the successive keys exactly equal. That's equal temperament roughly since the 19th century, which is a compromise. And to illustrate that, I play for you a chord alternating in equal temperament and with pure intervals. It starts with equal temperament. As you can hear, in equal temperament, there's much more fluctuation. Actually, it's a mess, which is not what you want, right? But to play all intervals equally out of tune, well, it is a solution. This is a representation of a temperament. So in the rows, there are the 12 keys, and in the columns are the 12 intervals. You can build on those keys. And here I visualized it as a heat map. So the darker the color, the more out of tune the interval is. And this is a heat map for a Pythagorean temperament in which all the fifths are pure, except for one. And as you can see, that has consequences for the in-tuneness of other intervals. This is Pythagorean temperament, but there are many more. There is a long history of searching for the optimal keyboard temperament. And basically there are 2 or 3 approaches during history. One is based on Pythagoras, which is theoretical, quantitative. And in this approach, the frequency ratios are exactly computed and then measured on a monochord, you can see here. And then the tone from the monochord is transferred to the instrument. But then you get calculations like this, which I'm not even going to pronounce, which are very hard to perform in practice, of course. The other approach is based on Aristoxenos. It's more empirical. It's like tune this fifth pure and then a little lower and check by your ear. And actually there's a third approach based on the Ptolemy, which says make as many intervals pure and don't use the others. So these are the main approaches. And in historical musicology, there is study to this practice, especially with the rise of historical performance practice, we want to know what were the historical tunings. So what are the sources for this? There are treatises, of course, theoretical treatises. There are tuning instructions, historical tuning instructions, surviving instruments. Some instruments are very old, but of course they often have been restored and altered. And there's a fourth kind of evidence which is hardly used, but which we can use, which is compositional practice. Because the composers knew which intervals to avoid and which intervals to favor, their scores contain information about the temperament practice. So, and of course, with MIR technology, we can access this kind of evidence. So now we can formulate our challenge, which is, given a suitable loss function, given interval occurrence rates from a corpus, some constraints, find a temperament that minimizes a loss function. This is our loss function. I don't have time here to go over all the terms, but the basic idea is to compute the mean squared error for all the 144 intervals compared to just temperament, to pure. And then weigh these intervals with the occurrence rates of the intervals in the corpus. So we need a minimization algorithm for this. We used 3, dual annealing, Bayesian hopping, and differential evolution, which we compare in our poster. And all 3 do not require a continuously differentiable loss function, which is in our case the case because of the min operator. So these are suitable procedures here. First, we calibrate our method. We created an artificial corpus, a synthetic corpus, based on C major. So we sampled intervals from a distribution that you would expect for a piece in C major, which has some C major, F major, G major, and A minor tonalities. And then we derived the optimal temperament for this, which is shown here. You have to read this as follows. The blue bars are the sizes of the fifths. So the first is the fifth on A flat, and then the fifth on E flat, etc. And as you can see, there are 4 fifths really out of tune in this solution. 2 are very low, 2 are very high, and the other fifths are about pure. But it doesn't matter because, of course, the fifth on A flat and the fifth on E flat is not used in a piece in C major. So as an illustration of this solution, I play you a synthesized version of the first prelude of the Multimedia Clavier by Bach, which is in C major, using this temperament. And to compare, if we transpose the temperament to E flat, for example, we get this. So here it gets a bit nasty, right? So there are many more papers on the web page we made with this paper. As a case study, we took Das Multimedia Clavier by Johann Sebastian Bach, which consists of 2 sets of preludes and fugues in all different keys. And the reason why this is an interesting case study is that we do not know exactly what Bach meant with well-tempered. Well-tempered means well-tempered, but he did not specify. There's a whole body of literature on this, with all kinds of speculations, what is the ideal Bach temperament. And there's even speculation that he encoded a temperament in the ornaments on the title page. So, yes. So this is a nice case to apply this framework. These are 3 solutions we find with our framework, with our method for the well-tempered clavier. This is the top one is an unconstrained solution, which shows a temperament with 1 low fifth, and the rest of the fifths are about pure. This is very similar to a temperament by Johann Philipp Kienberger, who was a student of Bach, so there might be a connection here. The second one is if we constrained all the fifths between 696 and 705 cents, then we get a more circular temperament. And this appears to be very similar to a temperament that was proposed by Herbert Kellertaat, a Bach scholar, in 1960, as ideal Bach temperament. And the third is if we only use 5-limit just intervals as targets, and then we get a temperament that is similar to equal. Of course, we can also compute our loss function for historical temperaments, which we did. And then if you sort this, you get this overview, and it's also on the poster. I can tell you more about that with the poster. That concludes my talk. Thank you, and I hope to see you at the poster.
Thank you, Peter. So the next talk is refining music sample identification with a self-supervised graph neural network. And the presenter is Aditya Bhattacharjee.
Hello, ISMIR. I'm Aditya. I'm from the Center for Digital Music at Queen Mary University of London. And I'm very excited to present our work, refining music sample identification with self-supervised graph neural network. So, firstly, the first order of business is to define what sampling is. So, sampling is a music production technique where a portion of an existing song, aka the sample, is incorporated into a new musical work. And the task at hand is the automatic identification of these samples, which can be quite a complex task given that a sample can be significantly altered during a sampling process. So, as mentioned in the title, we use graph neural networks as the neural architecture for neural encoders. And the reason to do that is the recent success in audio fingerprinting, which is a closely related task. So, we train this graph GNN encoder using contrastive learning, again, fairly common in contrastive learning. But then, we also train a cross-attention classifier, and which might seem a bit redundant at the moment, but I'll try to motivate this in this presentation. For the training data, we use artificially generated sample reference pairs, and again, we'll talk about this a little bit more in the poster session. During inference, we retrieve the matching reference in two stages. Given an audio query, we compute the audio fingerprint using our encoder, and we do an approximate nearest neighbor search to retrieve a set of coarse candidate matches. And that's where the classifier comes into the picture. We use the classifier scores to refine and re-rank these retrieved candidates. Another really important contribution of this paper is the extended annotations to the sample 100 dataset. So the sample 100 dataset is the only publicly available sample identification dataset. However, before this, you could not do segment-level matching. So what we did is we went about painstakingly getting the annotations for every single sample occurrence in both the query and reference track. And we have a bunch of other necessary metadata that might be useful for evaluation. So, we use the sample 100 dataset to evaluate sample identification, and we measure mean average precision and top one hit rates. And we compare with a recently released baseline by Spotify, which is a ResNet-based architecture. And our model performs competitively with the baseline model, but additionally, it has about 10% the trainable parameters as the baseline, and it's a lightweight alternative to that. And additionally, we also do other experiments, ablation studies on different kinds of samples, and we experiment with the length of queries. Come by a poster, we can talk about that a little bit more. So these are all of the contributions of our work. There's a lot more to talk about. We have released the code, the data set, as well as the trained models. Thank you for having me.
Thank you, Aditya. So the next talk is video-guided text-to-music generation using public domain movie collections. And the presenter is Zachary Novak.
Awesome. Good morning, everyone. Today I'm presenting on video-guided text-to-music generation using public domain movie collections. This work is led by Haven Kim, who couldn't be here. It's a collaboration between UCSD and Duke University and University of Michigan. So our main contribution is this open screen soundtrack library, which is a new data set of about around 700 music and video pairs from public domain films. It's about 37 hours. And the kind of nice things as to why you should use OSSL is, one, it's self-hosted. It is not one of those data sets where you go to the link and it says download from YouTube yourself. We have it directly hosted. You can go to the link at the end of the slides. We have a ton of annotations for mood and other sorts of captioning stuff. And it is both legally and ethically safe. This is all sourced from public domain movies. There are no copyrights here. Perfect for any sort of video to music generation tasks. And with OSSL, we also pair it with two evaluation sets. One, OES Pub, which is essentially just a held-out evaluation set, still being on soundtracks from open source and public domain movies, and also this commercial held-out set, which is about another 100 movies of actually modern commercial soundtracks that you should not train on. They are not viable to train on, but it's good to assess generalizability to sort of more modern music. And to give you an example of what it sounds like, I'll just sort of play you with some of what the video and soundtracks sound like.
Well, do you want to?
And the corresponding soundtrack. And it's important to note here that these are not source separated. We didn't want to contaminate our data set with maybe any sorts of biases that modern source separation models can use. These are all the soundtracks directly from the official soundtracks that we then pair. And to do this and to sort of construct OSSL, what we do is that we collect all the soundtracks that we could officially grab of the official soundtracks from these movies, and then we perform source separation on the raw movies themselves, and then use chroma similarity to detect, based on the source extracted music, where the corresponding real high-quality soundtrack is from, so that we can pair the video with the high-quality, not source-separated audio. And then to sort of show a proof of concept of what we can use OSSL for, we extend MusicGen, a modern text-to-music model with video controls, by adding a lightweight adapter following last year's audio prompt adapter work, which just adds lightweight controls using a pre-trained vision encoder to allow the model to condition its generative music on visual data from the video. And here's an example of one of the generations from our sort of proof of concept model. That's enough of that. So yes, please try OSSL. It is available here. It's completely open source. You can download it today and to come out to our poster for more information. Thank you.
Thank you, Zachary. So the next paper is PianoVAM, or PianoVAM, a multimodal piano performance dataset. The presenter is Yong-Hyun Kim.
Yeah, thank you. Hello, ISMIR. My name is Yong-Hyun Kim, and today I'm excited to present our work on PianoVAM. I would pronounce VAM, I don't know, but a multimodal piano performance dataset, and which is a joint project between KAIST and Georgia Tech. So what is PianoVAM? Well, it's a dataset with synchronized video, audio, MIDI, and also hand landmarks, fingering labels, and rich metadata. The key here is that we recorded amateur pianists during their actual daily practice, so the data reflects how the people actually really play during their practice sessions. So we created PianoVAM to push the boundaries of what's possible in this MIR field. And so what makes PianoVAM so special? Well, there are four main things. First is multimodal, and which with rich synchronized data streams, and also the detailed annotations, including hand tracking and also fingering labels. And the performances are pretty natural because we actually capture the performance on daily practice sessions. And also finally comes with rich metadata, not only for the performers, but also the pieces. So now let's look at the numbers here. So we have about 21 hours of recordings from 10 different performers. a quick comparison with Maestro dataset is that show like similar pitch and velocity like distributions, but we did find one interesting difference, which is like our pianists use the more sustained pedal, like damper pedal, much more frequently. And we believe that this could be like due to a few factors. For example, like the repertoire itself might be requiring some more like pedaling, or the performers might try to like struggle with compensating between the dry like studio acoustic conditions, or also it might be just like simply reflecting the natural playing style of the amateur pianists. So that was our like assumptions right now. And one of our key features is that the fingering data. So we developed a semi-automated like method to label fingerings with over like 95% precision with our curated test split. So the process is really simple, but it tracks hand landmarks first, and then we try to ignore hands which are floating, which means like the hands are not touching the keyboard, because that is useless for the fingering itself. And then the scores which finger is most likely to playing each note, we are calculating by the fingering score. And if there is a clear like single winner, then it is auto-labeled. If it's not, then we let the human annotator to like make the final call. And to demonstrate the utility of our data set, we quickly do the benchmark tests. So for audio-only piano transcription using our onset and frames model, we found that models trained on PianoVAM or a combined data set outperform the one trained only on the Maestro dataset if we test on the PianoVAM, which is really unsurprising, but it actually elaborates that maybe the transcription model can be kind of like dependent on what kind of like acoustic environments that has been encountered during the training phase. And also we also explored the audiovisual transcription by just like using the onset and frames model, but trying to be like doing like a post-processing by using detecting the hand landmarks and try to eliminate the outliers. So even just doing like that can actually improves the performance. So that was pretty awesome, and we are really looking forward to using this kind of modality for this piano transcription. So you can find more like code data and more on our GitHub page. And our team is already working on the follow-up studies. And we are also invite you all to explore this data set as well. So thank you for your attention, and I'll see you at the poster.
Thank you, Young-Kim. So the next paper is LoopGen, training-free loopable music generation. The presenter is Davide Mariazione.
Thank you. Hello, everyone. I am Davide Mariazione, PhD student at Sapienza University of Rome, and this is LoopGen. So, why loops? Well, the reason is because loops are pretty important to music, but currently state-of-the-art models are unable to give you audios that right out of the model are actually able to loop. So we tried to tackle this problem. The first thing we do is we take Magnet, which is a non-autoregressive audio model, and we modify its inference process by making it tiled. So we divide its context window into 3 parts, main tile and these 2 extremes, and then during the inference we copy the contents of this main tile onto the 2 extremes, such that the model is able to see both the start and the end of the track together. Next, what we do, since non-autoregressive audio models don't create such good quality music, is we modify a little bit the generation process by first making some hints using MusicGen, which is autoregressive and higher quality. In this way, we help Magnet create higher quality audios. Finally, since we've created audios already with MusicGen, is we modify the generation length. Instead of making it a fixed number like 10 seconds or 30 seconds, we make it dynamic. We calculate the bar length using bit.dis. We extract the bits from the hints, and we we ask Magnet to create, for example, in this case, 8 seconds or whatever is an integer number of bars, such that we create a higher rhythmic coherence in the track. Then we wanted to evaluate all of this. To do that, we employed perplexity, and we take perplexity just after the seam, right after that. In this way, we see how perplexing is the loop. And we see that indeed our model is 20 times lower perplexing than naively looping. Finally, we ran some listening tests with human evaluators, and we found out that by asking them how seamless, how audible the seam was in the loops, our model gave much more seamless samples. So in the end, we gave a way to, without retraining, create seamless loops. We also gave a metric to see how good these loops are, and we validate our technique using human evaluations. You can read more at the QR code. You can hear some clips. I'm sorry I couldn't really add clips in the presentation in the last days. But at any rate, you can hear them here, and I hope to see you at the poster session.
Thank you, David. So the next paper is Enhancing Music Recommender Systems with Multimedia Content, a context-aware approach. So the presenter is Bruce. Bruce?
Yes.
Yeah, okay.
Yes.
Bruce Verda. Let's start.
Hello, everybody. My name is Bruce, and today I'm presenting our work on how to enhance music recommender system with the addition of multimedia content. And it's a collaboration with Oleg, Veronica, Attia, and Marcus. A little bit about our motivation, where it comes from. We noticed that a lot of streaming services are basically providing users with an audio-only based experience. And of course, there are additional multimedia content available, like lyrics, music videos, additional images, but users need to manually search for it and engage with the service. So what we did is we tried to investigate how people listen to music, what their motivations are when they are reaching out for additional multimedia content, and we created some prototypes and tested whether the automatic addition of multimedia content actually increases the experience of people. Okay, so our research questions in a nutshell. We looked at what drives the different types of multimedia content usage and whether it actually improves the user experience when they are automatically added to the service. To answer our research questions, we conducted two different studies. The first study was a diary study in which we asked 26 participants over the course of a week to report back to us every time when they are listening to music, what the context is that they were in, what kind of multimedia content they were utilizing. And the analysis showed that we could divide them into 9 different kind of activity themes and 13 different uses and gratifications. So activity themes like household chores, working out, and motivations like to relax, to unwind, to motivate myself for working out. And what it also appears that they are directly connected to the type of multimedia content that they are reaching out to. So we used this information in our second user study, where we created 2 different prototypes, one with an audio-only based interface and one where additional multimedia content was added based on the context that users were in. So we had 59 people participating, and we ended up with a standardized questionnaire to evaluate the experience that people had. All right, so the key findings related to our research questions. We found that how users, the activity of users shapes what kind of multimedia content they are using, but also we found that the automatic addition of multimedia content significantly outperforms an audio-only based interface based on several subjective factors of the experience, like satisfaction, usefulness, and novelty. And this was also further confirmed based on some open questions that we had and some interviews that we had afterwards. People reported that they found it very useful and engaging, and they were quite satisfied with the automatic addition of the multimedia content. But they also noted that they can imagine that sometimes it can be very distracting in certain situations. So if somebody would want to implement such a thing, make sure that you have some functions to override, manually override this functionality to turn it off. So conclusions and future work. It was an exploratory study. In fact, it was a master's thesis project. So quite a limited amount of sample size. So we plan to, based on the promising results that we retrieve, we plan to extend this, but also looking at different cohorts and more fine-grained sensing. All right.
Thank you, Bruce. The next paper is CultureMERT, continuous pre-training for cross-cultural music representation learning. And the presenter is Agelos Nikolaos Kanatas.
Perfect. Hi everyone, I'm Angelos Nikolaos Kanatas, and today I will present to you our work CultureMERT, continual pre-training for cross-cultural music presentation learning, carried out in collaboration with Charailos Papaioannou and Alexandros Potamianos. So in this work, we introduced CultureMERT, a multicultural adapted version of the MERT Foundation model, which was originally trained on Western scenic data. And in order to achieve this, we explored two methods, continual pre-training and a model merging technique named task arithmetic, in order to adapt it to diverse musical traditions, including Greek, Indian, and Turkish traditional music. So most access foundation models for music have been trained primarily on Western scenic datasets, thus limiting their ability to represent diverse musical styles. As many musical traditions feature culture-specific characteristics, such as distinct rhythm patterns, improvisation, and microtonality elements, this can limit model applicability, and there's also a need for more inclusive and culture-aware models that go beyond Western-centric traditions. So the two methods we explore, continual pre-training and model merging, are promising adaptation strategies widely explored in other domains, but remain underexplored in MIR research. So our objective is to adapt the MERT model to non-Western traditions, while also preserving performance on Western benchmarks. Our proposed method is a two-stage continual pre-training strategy with learning rate rewarming, which stabilizes training, mitigates catastrophic forgetting, and enables effective adaptation under limited compute. We also explore an additional alternative approach based on model merging via task arithmetic, in which we algebraically merge single culture adapted models in weight space in order to create a unified multicultural one. So, our cultural adapted models outperform the base model on these non-Western music tagging tasks. For the non-Western traditions, we utilize Greek folk, Turkish makam, Hindustani, and Carnatic music, which we use for training and evaluating our models. To test the forgetting, we utilize the Magna Tegatune and FM medium datasets as the Western benchmarks. We develop a multicultural model trained on 650 hours of cultural diverse audio spanning all four non-Western traditions, as well as single culture models, each continued pre-trained on data from a single one, yielding the following models. And CultureMERT is the merged model constructed by combining the separately adapted single culture models through task vector addition and weight space. So there are several challenges associated with adapting foundation models with very limited compute. First of all, the large distribution shift can lead to catastrophic forgetting, while a naive adaptation such as training all parameters at once can lead to instability and poor adaptation. So our solution is a two-stage strategy that stabilizes it via learning rewarming and redecaying, as well as stage adaptation of the parameters. So more specifically, in stage one, we train on a subset of the data, updating only the CNN and feature excitement encoder embeddings, while freezing the transformer encoder. We also mix in 20% Western data for the music for all dataset in order to reduce gap and forgetting. For the learning rate, we use a model aggressive warm-up schedule. And in stage two, we unfreeze the transformer, continue training on the full dataset, and we use a less aggressive warm-up schedule in order if there is a trade-off between stability and plasticity. So, CultureMERT yields a plus 4.9 average improvement in ROC AUC on diverse non-Western music tagging tasks, with exhibiting minimal forgetting on Western ones. We observe that single culture models perform based on their in-domain tasks, while task arithmetic performs on par with multicultural continual training. We also explored that cross-cultural transferability varies across traditions, with transfer being asymmetric between the cultural adapted models. We also conduct a similarity analysis on the cultural datasets based on the Jensen sum divergence and cosine distance over their acoustic token distributions extracted from the neural codec model. Interestingly, these transfer patterns correlate with the acoustic tone level similarity, suggesting that such metrics can predict positive cross-cultural transfer. So to conclude, we introduced a multicultural adaptive music foundation model using continual pre-training and explored model merging for music-based lessons learning. In future, we plan to scale to more cultures, explore alternative model architectures, extend evaluation beyond data tagging, and conduct more detailed ablations. You can scan the QR code to read the full paper and explore our models of Hugging Face. I'd be happy to chat and share more details in our poster session. Thank you.
Thank you, Agelos. The next paper is Adaptive Path of Prediction, an unsupervised method for modeling node-level information hierarchy of polyphony. The presenter is Xiaoshan Wang.
Good morning, ISMIR. My name is Xiaoxuan, and I'm going to talk about how we use unsupervised learning to model the perceived information hierarchy of nodes in polyphony. This research was conducted with Martin Rochmeier at EPFL. So when we listen to a musical piece, especially for complex musical structure like polyphony, we don't listen to it just once. Instead, we need multiple listening to make sure that we make sense of the notes and understand the relationship between notes. So during this re-listening, we will automatically memorize some of the notes, but not all of the notes. And the memorized notes are not random. And our hypothesis is the memorized notes are informative so that they help us retrieve or predict other notes. This means that in multiple listening, our prediction is not purely left to right, autoregressive. Instead, it is more like connecting more and more notes to the existing network of anchor nodes. In this paper, we make use of this hypothesis to build our model. Our goal is to model a structural hierarchy of nodes in polyphony. By doing this, we want to develop a machine learning model of polyphony that can approximate the music understanding of active listeners or expert listeners. This will be useful for both the music theoretical development of polyphony and for understanding the polyphony perception. So how do we build such model? Our idea combines denoising diffusion and reinforcement learning. Instead of the traditional random data corruption process in denoising diffusion, we want to find a trajectory that better preserves information to the later stages of data corruption. Our model is built from two cooperating networks, a reduction network and a generative network. In each training iteration, the reduction network will propose different deletion paths. In each path, each step will delete one node until there's only one node left in the trajectory. The generative network will try to reconstruct from each of the paths, and if it can perform better reconstruction in one of the paths or some of the paths, this better performance will serve as a feedback, reinforcing the reduction network to learn to preserve the more informative nodes. Therefore, after training, the sample deletion path of the reduction network is directly a tagging of nodes importance. And those nodes preserved to the later stages are considered more important. And here's an example of our model's results. A is the original score, and in B, we visualize the top 50% of the nodes that our model identifies as important, and C is the expert reduction. We can see that both reductions converge on a very similar skeleton. The passing nodes are removed, and the strong beats are emphasized. In the poster session, we will show more of the example of the model's reduction. To summarize, we look into the cognitive phenomenon of re-listening, and we use this phenomenon to develop a model that can learn to find the structurally important nodes in polyphony. This model is one of the first unsupervised learning model of polyphony that try to approximate the music understanding of active listener or expert listeners. Thank you, and see you in the poster session.
Thank you, Xiaoshan. The next paper is Versatile Symbolic Music for Music Modeling via Function Alignment. The presenter is Junyang Jiang.
Thank you. Hello, everyone. Welcome to the presentation of the paper Versatile Symbolic Music for Music Modeling via Function Alignment. I'm Junyang Jiang. Before we start, I will first show you a demo from the MIDI drum condition generation task. The input is a drum track with the beginning of the song, like this. We ask the model to generate a complete song. So here's the model's output. So you can hear that the structural coherence between the input condition and output music. So how do we do this? Let's first focus on transfer learning for language models. These models are often used to fine-tune downstream tasks. For music analysis tasks, like chord recognition, people typically use probing. And in controllable music generation tasks, like chord condition generation, people often use adapters to inject the condition into language models. One thing we observed is that many music features can be represented by the music modality itself. For example, we can use specific drum patterns to represent beats and downbeats, and the block chords notes to represent a chord symbol. This allows us to unify a wide range of music analysis and conditional generation tasks by regarding both inputs and outputs as music. This is the core idea behind the music for music modeling. Under this setting, both the input and output can utilize the knowledge from the pre-trained music language model. We can insert a lightweight adapter between these two pre-trained models to create an interference between the input and output sequence. This is the main idea of our model design. We name our model after a new theory of mind called function alignment, which believes the emergence of human-like intelligence comes from the dynamic synergy among interacting agents, like the sparse connection connecting our left brain and our right brain. In our model, we use parameter-efficient adapters to achieve such synergy. We start with two language models without any interference, and insert a lightweight adapter using a cross-attention layer. We also have a self-attentive variant of this adapter. We fine-tune our pre-trained MIDI language model on 5 different tasks, including both conditional generation and music analysis tasks. Subjective evaluation shows that our model achieves impressive performance compared to baselines, and sometimes even achieve better musicality compared to original ground truth, which is really cool. For music analysis tasks, the model also achieves good results on MIDI chord recognition. Notice that this model only requires fewer than 100 sounds to achieve this result, which is very nice. But here's a spoiler. As a follow-up work, we had a paper in this year's late-breaking demo that achieves an even better performance with no supervised label at all. If you are interested, be sure to check both the poster in today's section and our late-breaking demo poster session on Thursday. Thank you.
Thank you, Julian. The next paper is Understanding Performance Limitations in Automatic Drum Transcription. And the presenter is Philip Fayez.
Yeah, hi, I'm Philip, and I'm happy to present this paper here at ISMIR. I wrote this paper together with Christian Uhle, Meinert Müller, and Matthias Lang. The motivation for this paper was that we currently see in state-of-the-art algorithms for automatic drum transcription that the global performance is high, but still the performance of single classes, such as toms and cymbals, is still limited. So that's why we had a look at certain challenges that we and other people believe to be key challenges that might contribute to this non-ideal performance. This is, for instance, interference from melodic instruments and vocals. Then usually we have overlapping drum sounds, which of course complicates the transcription. We have weak onsets, which are difficult to detect due to low loudness. And also when we train neural networks for ADT, the generalization capabilities are of course limited. So here in this paper, we systematically investigate and quantify the impact of these key challenges. To do this, we use our star drums dataset that we recently published as a ISMIR paper. This dataset includes synthesized drum sounds mixed with real recordings of melodic instruments and vocals. And yeah, as this drum set includes synthesized drum sounds, we have full control over the content of the drum stem which is used in this dataset. And we use this property to create versions of the dataset that eliminate specific key challenges. So, for instance, to reduce the diversity of drum sounds so that our model does not have to generalize to that many different drum sounds, we created versions where we use a lower number of virtual drum kits to render the drum sounds. So the baseline uses 20 drum kits, and we created versions using 10 and a single drum kit. Furthermore, we created versions without weak onsets and without simultaneous onsets, and we carried out all experiments with and without the presence of melodic instruments. We did the experiments for 3 different DNN architectures to show that the results do not only apply for one architecture. We transcribe 8 classes, as you can see here, and in the evaluation we use a 50 milliseconds tolerance window, and in the end we compare global F measures computed using micro-averaging. So this slide very briefly summarizes the main findings. In this table we can see relative performance changes. So for this we averaged the global F measures of the 3 architectures and then divided the average F measures to obtain this relative performance change. And in the first line we can see that when we reduce the number of drum kits in training from 20 to 1 and test with the same drum sounds in testing, then we can see an increase of performance of 5% for DTM, so for drum transcription in the presence of melodic instruments, and a lower performance increase of 1.6% for DTD, which is drum transcription of drum-only recordings. We can see a similar improvement when there are no weak onsets present by 5.5% for DTM and 1.1% for DTD. And when there are no simultaneous onsets, we can see again a similar 5% performance increase for DTM, but a much higher increase of 8.5% for DTD. Yeah, unsurprisingly, the highest performance improvement was obtained when there are no sounds of melodic instruments in singing present. So this improved performance by 14.5% on average. So in this paper, we provide a quantification of factors limiting ADT performance, and by providing these numbers, we hope to support future developments by providing clear indications how addressing these key challenges can improve performance. Thank you, and see you at the poster session.
Thank you, Philip. The next presentation is high-resolution sustained pedal depth estimation from piano audio across room acoustics. And the talk will be presented by Han-Wen Tang and Kun Fang.
Good morning, everyone. My name is Kun, and this is Han-Wen. We are presenting our work, high-resolution sustained pedal depth estimation from piano audio across room acoustics, in collaboration with Stu Wang and Ichiro Fujinaga. Although the sustained pedal is a continuous control essential for producing nuanced sound effects in classical piano playing, previous studies have largely treated it as an auxiliary signal in piano transcription systems, focusing primarily on binary on-off detection. So in this work, we predict pedal depth as a continuous value and investigate how model predictions vary across different acoustic environments. Our robustness experiments also result in the creation of a synthetic audio dataset. Our model takes log-mel spectrograms and MFCCs as input, which goes through a convolutional front end and then a transformer encoder. The model outputs pedal depth values between 0 and 1 per frame, binary onset and offset sequences, and global depth value averaging each segment. We compare our model's performance with previous studies. In the conventional binary pedal on-off scenario, our model achieves comparable scores. For the 4-class classification task corresponding to the 4 pedaling levels commonly described in piano pedagogy, our model has higher F1 scores. Regression metrics further confirm that our prediction errors are lower. Moreover, when evaluating accuracy under small tolerances, our model outperforms baseline starting at a threshold of 0.15.
Here are 3 examples of piano pedaling in performance, and the first one is rapid full pedal change, the second one is half pedaling, and the third one is fluttering. And the blue dashed line is a ground truth which has nuanced changes over time that the red-colored baseline fails to capture. Our model predictions is plotted in yellow, and as we can see, it closely follows the actual curves. We used not only the real audio recordings from the Maestro dataset, we also take the performance MIDI and synthesized audio recordings in 4 different room settings for robustness analysis using piano tech. Unfortunately, all existing models struggle to generalize to synthetic rooms. To further investigate, we conduct a leave one out experiment. So as expected, the performance is consistently worse on unseen rooms. However, trading with acoustic diversity leads to better model generalization to new environment R4. Across rooms with increasing reverb, the pedal value distribution for ground truth is the same, and it should be. However, when training on real recordings only, we see an upward drift. And this means that when there's more reverb, the model tends to predict deeper pedal usage. Now, when we train on a mixture of rooms, we see that the predicted distributions are back in line. This shows that the acoustic diversity in training can help make more consistent estimates. To conclude, we show that it's very important to do continuous estimation for piano sustained pedal depths, and it leads to finer and more musically meaningful analysis. And we also show that models seems to be reverb sensitive, and training with acoustic diversity helps. Thank you very much.
Thank you.
Thank you. The next paper is investigating an overfitting and degeneration phenomenon in self-supervised multi-pitch estimation, and the presenter is Frank Switkowitz.
Hello, everyone. My name is Frank Switkowitz, and in this short presentation, I'll be introducing our work investigating an overfitting and degeneration phenomenon in self-supervised multi-pitch estimation. So previous work has shown that self-supervised objectives can significantly improve both, or I should say they are quite effective for monophonic and polyphonic pitch estimation. These objectives are typically based on pitch invariant or pitch equivariant transforms, and the models generate implicit pitch salience grams. However, when attempting to generalize these self-supervised objectives from monophonic to polyphonic audio, it becomes increasingly difficult to protect against the model predicting trivial solutions. In our previous work, we circumvented this issue by leveraging energy-based objectives in a sort of reconstruction paradigm with respect to the input energy. In this work, we hypothesize that this energy-based protocol can be replaced by a small amount of supervision on annotated data. So we adopt the same framework we used as in previous work. This consists of computing a harmonic constant Q transform, feeding this into a fully convolutional model, and producing what we consider to be a multi-pitch salience gram. In this work, we conduct supervision using the URMP dataset, which includes annotations for pitch, and we incorporate 2 additional sets of objectives. So the first set is based on pitch invariant transforms. So these would include like random equalization or random additive percussion. And our objective is formulated such that the output of the model given these transforms is trained to match the output of the original audio. Our other set is our equivariance objective based on pitch equivariant transformations. These would include time or frequency shifts as well as stretches in time. And this objective is formulated such that the output of the model given these transformations is trained to match a parallel transformation of the output for the original audio. So here we show some results. These are only on URMP, our annotated data set where we train with both supervision and self-supervision. Here we have in white pure supervision. Red is supervision as well as random equalization with the invariance objective. Green is supervision plus additive percussion. Blue is supervision plus our equivariance objective, and black is all of them. So we can see that in this case, the self-supervised objectives have nice potential to improve performance. This is mostly attributed to the equivariance objective. However, the problem arises when we attempt to extend the self-supervised objectives beyond the supervised data set to arbitrary data sets. And what we see when we try this, in this case on 3 separate data sets, NSynth, MusicNet, and Free Music Archive, what we see is that the performance basically collapses for any distribution of data that is does not have corresponding supervision. But meanwhile, our supervised data set URMP stays consistent with the results. We can also see when we fine-tune our URMP only model, the best one, that over training, the activations slowly fade away, drifting towards a trivial solution. So thank you very much for listening, and I look forward to discussions and questions in the poster session. I will see you there.
Thank you, Frank. The next paper is Sheet Music Benchmark, Standardized Optical Music Recognition Evaluation, and the presenter is Juan Carlos Martinez Sevilla.
Yeah, thank you, Mr. Nakamura. Hello, everyone, and good morning. Well, this work has been possible thanks to my mates at the University of Alicante, Joan, Noelia, David, and Jorge, the ex-Apple engineer Greg Chapman, and the current Stanford professor Craig Sapp. So first, given the number of attendees that work on audio, I wanted to show you how a music score image looks like. And in order to get your desired audio files, you must use an OMR pipeline. So you get a structured format, such as Kern, MEI, or Music XML, to synthesize it into an audio file. But I also wanted to highlight the importance of, well, this is not the presentation, this is the other one, but it's okay, I'll keep talking. Yeah, it's fine. So I wanted to highlight the importance of using benchmarks in many fields, or the existence of benchmarks. So for example, in audio transcription, you guys have MAPS or Maestro. In genre classification, you have GTSAN. And we believe that in the future, for multimodal music understanding, datasets or benchmarks like Mutual Music will be really helpful. But what about in OMR? Well, here I have also HTR dataset, handwritten text recognition. Yeah. But what about in OMR? Well, that is why we present the first OMR benchmark in Common Western modern notation, that it spans for four music textures, such as quartet, piano form, polyphony, and, well, other that includes, for example, vocal music. So the key thing here is that it is suitable for modern OMR pipelines. So you can test here in the benchmark your layout analysis models, your line level transcription, and your full page or page level transcription. I also wanted to highlight that, well, the dataset is 685 pages of size, and we focused on cleaning the encoding because we've picked or we choose to encode everything in kern. So we managed to standardize, but we keep the raw format, the kern, and the ekern, which is a sort of tokenization, so we can reduce the vocabulary size. Together with the benchmark, we also released the OMR normalized edit distance. And this is key for the work because it allows something that traditional metrics using OMR couldn't do, which is locating with the metric where the errors come from. So here I'm showing a brief example. And as you can see, traditional metrics like the symbol error rate, which is just a simple and easy to use edit distance, shows a 9% error. But the thing with OMR is that it can divide the error in different categories. So we can see, given the total error, where it comes from. In this case, for example, 65% of the total error amount of errors are from notes, and 35% comes from lyrics. So if you are interested in OMR, benchmark, and these new metric, please come to the poster to talk a little bit. Yeah, thank you.
Thank you, Juan. So the next paper is FX Encoder++, extracting instrument-wise audio effects representations from mixtures. The presenter is Yen-Tung Ye.
Okay. Hi there, I'm Yen-Tung from National Taiwan University, and today I'm going to present the work FX Encoder++. This is the work done during the internship at Sony. So our motivation is that audio effects representation are useful when developing the intelligent music production system, such as audio production style transfer, effects modeling, or production style retrieval, and more. So that's why we want to develop the model that can help us get this kind of representations. So this is our proposed model called FX Encoder. Our core idea is using an extraction module trained with two-level contrastive objectives. So let's take two stems as an example to showcase our training objective. As illustrated in the slides, our approach begins with two source stems. Let's take drums and guitar specifically in this slide. And we split each stem into half and creating two pairs. And the first pair containing the initial segments of drums and guitar, and the other pairs contain the remaining segments. And then in next step, for each pair, we will apply the same audio effect chains to the corresponding instruments. So specifically, both drum stems receive identical processing, and as shown in the green audio effect chain here. And for both guitar, they also process with the identical audio effect chain, as shown in the pink here. And then we will process them together to create the final mixture audio. And this procedure will use two mixtures that share the same instrumentation, same audio effect characteristics, but different musical contents. And that's what we want. Like, we want our encoder to focus only on the audio effects information. So our first training objective is to maximize the agreement between the latent representation of these two mixtures using the Sinclair-based contrastive learning. So in the picture, I will try to maximize agreement between the mixture latent 1 and mixture latent 2. And in the next stage, to further enhance the model's understanding of the instrument-specific wise, we will use an extractor guided by the query vector to get the instrument latent 1. And why do we want to do this is because in most of cases, we only have the mixture, but if we want to know the audio effects information from the stem-wise, one possible way is to use the source separation, but if we do not have the good enough source separation, or if we do not have the universal source separation model, then it is hard to get that. So we try to model that stem-specific audio effect information from the embedding space. And simultaneously, another encoder will extract the stem level audio effect information also from the other guitar track. So we can try to maximize the agreement also from the instrument latent 1 and instrument latent 2. And that is our model. And the evaluation setup is that we're choosing some general purpose models such as CLAP, PEN, VGG-ish. And also we use two well-proposed audio effects representation model called FX encoder and FX rep. And we evaluate our data, we evaluate our model from MuseDB and MedleyDB. So this is our evaluation table. We try to evaluate our model like we want to get the same production style but different musical content, which means we want to get the clips that process with the same audio effects but different plain musical content. And as we can see in the table, our model have the best performance across all retrieval scenarios. And interestingly is that the vocal performs worse when comparing to drums and bass. And we think this is probably because of the high timbre complexity. So this tells us the information that timbre and audio effects are somehow correlated with others, and we need some further discussion about this. And then we also try to evaluate our models through the instrument-wide specific evaluation. And one way is that we try to evaluate our model against the source separation, because we can use source separation to get the same information. And unfortunately, we lose the high quality four-stem source separation model. But good news is that when comparing to a universal source separation model, our model performs better. So the conclusion is that we have the one new audio effects representations, and it can use for many potential applications. And it will be happy to see you in our poster for discussion, these kind of things. Thanks.
Thank you, Yenton. So the next talk is a ISMIR paper presentation, and the title is Predicting Eurovision Song Contest Results, a Hit Song Science Approach. And the presenter is Katarzyna Adamska.
Thank you. Hello, ISMIR, and special hello to any Eurovision fans in the room. I'm Kasia, I'm from Center for Digital Music, and I'm presenting the paper Predicting Eurovision Song Contest Results, a Hit Song Science Approach. It was published in ISMIR earlier this year and co-authored by my supervisor, Joshua Rees. So Hit Song Science. It assumes that popular songs share musical, cultural, and contextual traits. But prediction tasks in Hit Song Science often face bias from choices like which songs are studied or how popularity is defined. So Eurovision, one of the world's most watched song contests, offers a unique controlled test case. With a specific list of songs, clear success metrics from jury and the public, it helps minimize these common biases. So Eurovision consists of 3 events, 2 semifinals and a grand final. Not all songs compete in the same show, so our prediction framework must reflect this format. That's why we predict the semifinal and grand final results separately. I would also like to give a shout out to the Mirovision dataset, which was presented at ISMIR 2 years ago, because it was a massive help preparing data for this project. To predict Eurovision, we tested 7 different feature sets using contest data from 2008 to 2024. Our framework essentially integrates 3 types of information. The intrinsic song features represented by audio and lyrics, public appeal measures such as YouTube daily views, and contest-specific factors, which are performance order, previous year's vote ratios, and vote reciprocation between countries, because this allows for voting partnerships. We run out hold one out experiments, testing each of the years from the period between 2008 and 2024 against the others, implemented XGBoost regression and evaluated the performance with R2, rank correlations and average rank errors. And we asked the question, which of the 7 approaches best predicts Eurovision outcomes across both semifinals and grand finals over the years. So what did we find? Song features alone, audio and lyrics, were weak predictors. They explained very little variance. Public appeal, which was measured by the YouTube views, was a significant factor. However, it was possibly biased due to the post-contest exposure. The best results came from combining all three domains, the song, public, and contest factors, as this approach performed the most consistently across both semifinals, finals, over all the tested years. What is also really interesting, we found that the audio features that were used in this study, extracted using the Essentia music extractor tool, correlated more strongly with YouTube daily views rather than the Eurovision rankings. This suggests that perhaps some pitch or timbre characteristics may influence public appeal, especially in perceptual scales like Mel and Bach. So in other words, there may be certain song qualities that may drive audience engagement, even if they don't translate into contest success. So the main takeaway is clear. Eurovision's success cannot be explained by the song alone. It emerges from the intersection of the song's characteristics, audience engagement, and the unique dynamics of the contest itself. Our findings also suggest that there might be different variables affecting short or long-term success of a song. So yes, thank you very much, and if you're interested, please come speak to me at the, next to my poster, and you can scan the QR code for the project GitHub page. Thank you.
Thank you, Kasia. The next and the last presentation is also a ISMIR paper presentation, and the title is the Giga MIDI Dataset with Features for Expressive Music Performance Detection. This will be the video presentation presented by Kyunju Lee.
Hello, ISMIR community. My name is Kyunju Maverick Lee from the Meta Creation Lab for Creative AI in the School of Interactive Arts and Technology at Simon Fraser University in Canada. Today, I will be presenting our ISMIR paper on the GigaMIDI dataset, the largest symbolic music dataset with new features for detecting expressive music performance. Here's a quick roadmap of today's talk. We'll start with symbolic music and MIDI and then compare non-expressive and expressive tracks. After that, we introduce the GigaMIDI dataset and explain our heuristics and thresholding process. Lastly, we finish with evaluation results and conclusions. This table compares existing symbolic music datasets. Most are small or instrument-specific. For example, Maestro is piano only and Group MIDI is drums only. In contrast, GigaMIDI is much larger with over 1.4 million MIDI files across all general MIDI instruments. This makes it uniquely suited for large-scale MIR and generative music research. Figure 1 illustrates our 4 categories: non-expressive, expressive onset, expressive velocity, and expressively performed. Non-expressive tracks are quantized and flat, while expressive tracks show microtiming and velocity variations. These distinctions form the basis for our detection heuristics. Figure 2 shows the distribution of track durations. Drum tracks are typically short loops, while piano tracks span a wider range of bars. Table 2 breaks down the note events by instrument group. Over 77% come from piano and drums, reflecting how this instrument dominates MIDI usage. This scale and variety make GigaMIDI a powerful research resource. Here's a heuristic one, which measures distinctive note velocity ratio and onset deviation ratio. DNVR captures expressive variation in dynamics, while DNODR captures microtiming deviations. Together, they provide a first-pass method to detect expressiveness at the track level. Figure 6 illustrates our second heuristic, the note onset median metric level, or NOMML for short. It assigns each note onset to a metric grid, such as duple or triplet subdivisions, and takes the median. Human performances often fall outside strict grids, so a high NOMML value is a strong signal of expressive timing. To separate expressive from non-expressive tracks, we selected optimal thresholds. Using curated ground truth data and logistic regression, we maximized the P4 metric, which balances true positives and true negatives. For NOMML, the optimal threshold was level 12, giving us the cleanest separation. Tables 6 and 7 summarize our evaluation. NOMML outperformed all other heuristics, achieving 100% classification accuracy. It also achieved a perfect correct negative rate, meaning it reliably distinguished non-expressive from expressive tracks. Figure 7a shows the distribution of NOMML results. About 69% of tracks are non-expressive, while 31% are expressive. Figure 7b shows instrument breakdown in the expressive subset, where piano and drums dominate. Altogether, we curated 1.65 million expressive tracks, making this the largest expressive MIDI dataset. That was a quick summary of our ISMIR journal paper presentation. And if you are interested in more details, please check the Hugging Face Hub webpage and the full ISMIR paper. Thank you for listening.
Okay, so now it's a time for a coffee break. So please go to the poster session in the seminar room afterwards. So, okay, so let's close the session by thanking all the presenters again, and also volunteers and all the organizers for their wonderful jobs. Thank you.